So if you look on question number 10, okay? So this is kind of unique, you kind of got to visualize this. So here's this wire, right? So because of the, if you look at this in terms of that X, so you kind of got to visualize this. So here's this wire like this, and you're looking down from on top, okay? And so here's a wire, and you're in an external magnetic field that's going this way. So you have two magnetic fields. One that's going to be created by the wire, because there's a current. And then the also, like, this is a magnet, and I'm holding the magnet here, okay? So you have two different magnetic fields. One created by the current, one created by the magnet itself. So you're told that at point 1, that the net magnetic field at that point is 0. So if you think about that, that should kind of be able to visualize this. So it's like a vector, right? So here's your wire, and that current is going into the wire. So here's the wire, so you put your thumb in this direction. Then you're going to wrap your hand around like this, so this current is creating a magnetic field that's going down at that point. That's going to hit this magnetic field going this way, and it's going to be a vector sum of 0, okay? So it would be like, it's a tug of war. Kyle's pulling this way, I'm pulling that way, the net effect is going to be 0, okay? Got that? Now, up here, you still have a magnetic field going like this, right? But now, if you put your hand this way, up there at the top, the current from this wire is going to be going like this. You have this magnetic field going up like this. So you have a magnetic field across, so it's just like you have two forces going on. You have a force going this way, and you have a force going this way. The net effect is going to be going up like this, okay? You got that? You have that visual, okay? So one's across, one's going up, boom, tip to tail, draw the resultant. Now, 11's a little bit trickier, okay? So 11's a bit trickier, mainly because of the fact that you have two wires. So there's number 10. So in number 11, you have one wire coming across like this with a current going in this direction. And that's the bottom wire. And then on the top, okay, you have the current going in this direction, okay? So if you start with the top wire, okay, with that current going like this, so it's coming down like this, so it's either going into the page on this side, or it's coming out of the page over here, okay? So you're going down, boink, doink, X's, dots. Now the bottom wire is coming across like this, so that current's going in this direction, so that one's coming out of the page here, and it's going into the page over here, okay? So you're going doink, doink, boom, dots, X's. So what they're asking for on that one is that in which direction is the magnetic field at a point halfway in between them. So you kind of got to do like a visual about this. So you have these two wires like this, and you're talking about that point in between. So what you should see, and this is going to be tough to hold these with the right hand rule all at the same time. So you got one in effect going like this, okay? So visualize this. So that's going to be either going in this direction, but it's going to be coming somewhere in this plane. And then this one's going to be going like this, like that. So you have one coming this way, and you have another one going like that, okay? So it's going to be a similar idea to what's going to happen on number 11, okay? So both of those on 10 and 11, you're going to end up with two vectors at right angles and a resultant. So what you want to do on 11, make sure that you indicate which direction this thing is going from that perspective. You might even label like which one is the magnetic field from the top, which one is the magnetic field from the bottom. That might help you kind of see that visual. Okay. When you get to 15, because 15, I got to make sure that you get 15 because this is going to form the basis of today's lecture. So in number 15, you've got positively charged particle going into a magnetic field like this. So what's the significance of the X's? Okay, so if you take and point your thumb in the direction of the particle is moving, so it's going like this. The magnetic field is going into the page, so your fingers point upward. So what they're asking for is what's going to happen to that initial direction. So this is a positively charged particle. The magnetic field is going like this. Fingers point up. So this thing is going to get deflected towards the top of the page. Okay? Got that idea? Cool? Beautiful. Now, if it had been an electron, what would have happened? So,
The shiny.
Opposite direction.
you can either do one of two things. You could do the left-hand rule and take your thumb pointing in that direction. The magnetic field is going into the page and your fingers point downward, okay, if you like the left-hand rule. Or it's just the opposite of the right-hand rule, okay? Whichever method works for you, I care not, okay? Just pick one. Now, when you get to, like for example, on number 16, when you're asked to give that direction, describe them the force charge after they enter the magnetic field is shown, right? So with this one, you know, make sure that you're kind of saying, is it up, is it down, is like into the page, is it out of the page? Because 17 is a little bit trickier. Because in 17, you kind of have to work backwards, and you have to figure out the magnetic field direction. So on this one, you have to figure out which direction your index finger is going to point. Okay, so you up to this point, you've been given the thumb, the index finger, and you figure out the direction that your fingers are going to point. On this one, you're giving the thumb, the fingers, and you figure out which direction your index finger points. So it's just kind of the opposite, but it's the exact same idea. So just be specific on 17. So let me give you a hint. Like 17A is either into the page or out of the page. Don't tell me like up or down. Okay? So it's either into the page or out of the page. Not up, down. Okay. Now, let's talk about the problems. Because it's interesting when you get to question number 8. Okay? So, and the whole key to this is that the evidence is weak, that typical high voltage transmission line is 20 meters off the ground and carries a current of 200 amps. Estimate the magnetic field strength on the ground underneath such a line. Okay? So on my property, on the north end of our property, I've got these big, huge transmission lines like this. Okay? And everybody flips out and go, oh my God, there's a magnetic field around it. Okay, you're right, there is. Okay, because there's a current. Okay, there's going to be a magnetic field. So what you see if you do this math right on number 8, you should see that the value of that magnetic field is like 2 times 10 to the negative 6th, which is 4% of the Earth's magnetic field. Okay, so me standing underneath that wire is I'm only getting 4% of the normal magnetic field I would get from the Earth. So it's just like
A nice healthy 104%.
Huh?
Nice healthy 104%.
Yeah. So it's just like relative to that of the Earth. But then what I wanted you to see then on number 9 is that your answer to number 9 is also 4%. Okay?
Well, it depends.
So, I mean, so if you're sleeping underneath an electric blanket, which you're gonna sleep all night, okay? That's gonna be subjected to the same magnetic field as me standing underneath a 200 amp transmission line. And nobody thinks anything about sleeping underneath an electric blanket. So I just tell you that, just so that you have some perspective.
I got exactly 4%.
Oh, that's bad, it's a magnetic field.
I got
It's the
exactly
same magnetic field if you sleep underneath an electric blanket, for God's sake, okay?
How far are you assuming?
Huh?
How far are you assuming?
That's 10 centimeters.
All right.
So, there's that.
I think that's correct.
Anyway, so let's talk about question 21, just from a historical perspective, okay? So, if you hearken back to your Chem 1 days, and by the way, I've got to teach the Chem 1 honors next year, so that'll be interesting.
There can be freshmen in those.
No, there won't be.
I was in Kim my
Shut it.
freshman year.
Shut it, Zippy.
I did.
I would have hurt you, physically
There
hurt you.
literally can be.
Okay?
Emotionally,
Skippy freshman
physically.
year.
Oh, God, no,
My
that,
sister
such
did.
bad things would have happened. It would have been horrible. So, again, you have to view the Moore model from like a historical perspective, okay? So, this is after Ernest Rutherford. Ernest Rutherford did his work, shot the alpha particles at the gold foil experiment, found out that the nucleus was like 99% of the mass, but it only can occupied like 0.1% of the volume. So they concluded that the atom is 99% empty space. So they said, oh, and keep in mind, these are all physicists. The chemistry department had nothing to do with this. Okay, this is all being done in the physics department. Chemistry department claims it. Says, oh, let's talk about atoms. It was like, really? You guys were figuring out how to make cocaine.
They're just
We were
jealous.
doing the hard work.
They're just jealous.
They were just jealous. And
Crackhead.
so they said, wow. So in their mind, they thought, oh, an electron orbiting the nucleus would be the same model as planets orbiting the sun. Okay? Seemed reasonable, because they were all physicists and they had studied Newtonian laws of motion. So, sun, planets, nucleus, electrons. Same idea. Until they started doing the math, and then it just all went downhill from there. So, what I want you to see on 21 is that if you look at this in terms of your radius, 5.3 times 10 to the negative 11th, which is really, 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 really small. Because if you consider like a human hair has a thickness of about 10 to the negative 4th, okay? That's the thickness of a human hair, okay? So this is like 10 to the negative 11th, which is like a magnitude of 7 times smaller than the radius of a human hair, okay? Which is cool. Atoms are small. It'd be awkward if they were big, okay? They're small. It's cool, okay? So 2.2 times 10 to the 6 meters per second, which is Hall in the mail, okay? If you remember, satellites orbit at like 10 to the 3rd meters per second. So this is like 10 to the 6. So electrons are moving at about 1,000 times faster than orbiting satellites are, okay? It's a different speed. So what's the magnetic field at the center of a hydrogen due to the motion of the electrons? Okay, so basically what you want to do is you can look at this, go, okay, V equals 2 pi r over t. You have the radius, you have the velocity, and then you can figure out the amount of time for one rotation, if you really want to do the smash mouth physics. Or you can kind of circumvent that a little bit and go current equals Q over T, and you can put that in there. And what you'll see if you do this right, you get a current of 1.06 times 10 to the negative 3rd amps, okay, which doesn't seem like a lot until you plug it into like a magnetic field, and then plug that into B equals mu naught I over 2R, and we're gonna use 2R because it's like a closed loop. We're not gonna use 2 pi R because it isn't a wire. And if you do that, you get like about 13 Tesla. What?
Why can't we use the MV over QB equals R?
I suppose you could.
Because I did and I got a different answer.
I tried that first and it didn't work.
What? So you set. You're assuming that centripetal force is equal to that magnetic field, and that's not necessarily true here. That's why you just have to go off the information that was given in the problem. Because you're trying to find the magnetic field at the center, not like an external magnetic field. That's why it won't work. So, anyway, so you get like 13 Tesla, okay? So, the Earth's magnetic field, right, is like 5 times 10 to the negative fifth. So this is like 12.6. So this magnetic field would be like 10,000 times stronger than the Earth's magnetic field, which would mean that we would be basically really, 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 really strong magnets. And that would be in one atom. Imagine that you have all of your atoms like that. Basically, it would just get so weird so fast. So basically what they figured out is that this sounds cool, but the math doesn't work. So we can't treat it as like a magnetic field situation. Anyway, on 26, what's the frequency of circular orbit, electron or proton? So what you should see on 26 is that the electrons is something times 10 to the 6th hertz on A, and then the proton is around 800 hertz.
I think I did it right.
And hopefully your answers on 25, because 25 builds off each other. Hopefully you realize that because the electron has much smaller mass, that's why those distances are so far apart.
Did you do butt stuff?
Anyway, so are we good?
Like angular
I-
velocity.
Yeah.
Which one? Problem
I used
22?
the force and triple.
Okay.
I mean angular velocity.
Just
Not what I said, bro.
What did you think about, or do I want to know?
Probably not. I didn't think about anything. That was the issue. I used angular velocity, and I was just wondering if Brady used the same method.
yeah, pretty much.
Okay, so on 22, beginnings of 22 is fairly straightforward, okay? You're just going to use QVB sine theta as single proton. You know the charge on a proton. They gave you the velocity and the magnetic field, and it's a 45-degree angle, okay? So this is a situation where this is where you have to take that angle into account, okay, because it's at a 45-degree angle. So then, the second part, then, B, because the magnetic field is parallel with that, so if you plug in like that angle, that on that second part there is no force because that movement is parallel with the magnetic field. So your answer to 22A should be something times 10 to the negative 13th. And make sure you give the direction on that. There is 2 parts to that, okay? What is the magnitude of the force? Give your answer as a magnitude and a direction. So you should have a value and a direction
Right?
on 22A.
Did you get right up? Right up?
Anything else? Once? Twice? So get that handed in.
choke on the opposite. Just let him go.
Generally good advice.
Continue to not follow it. I speak off of reaction.
I feel like you'd give great life advice based off your mistakes.
What?
Half a second to think.
Think before you speak. I speak off of reaction. I think of it.
Do you know? That's not obvious at all.
Probably.
It's alright, the comments breaking up.
Exactly. It's nice to be able to just breathe in a bit.
Yeah, breathing in life.
Freaking back.
I kept getting golden truffle, and I wanted to break my fingers.
Is it
You
this?
get a kill with an elemental weapon, and then if you use the ability to that same element, it gets like a buff.
I didn't
It's
know.
like really bad.
It's kind of a very situational. Oh, on your
Yeah, I kept getting that, and then like stupid stuff with Snapchat. I wouldn't be alright. I'd be okay with it because I'd have to get two options on the
But
damage,
it's not.
but I kept getting golden truffle.
Yeah, I
and
just
something
it's
stupid.
this hamster.
In Snapchat.
Yeah, I just want something good, but then something okay.
I don't know. I got this for my
Perpetual motion, I think, is pretty
So that way.
Yeah,
Hello.
perpetual motion.
good.
Man,
Moving
what?
target's better, but perpetual motion still really pretty good.
I don't know, like
And
fingers
tell
can
me-
do it, right?
So, can I not?
Compulsive reload.
So if these are the 90
That's
degree
people
angles,
compare it's the stupidest perk because
he's going this way.
weapons have such a low ammo capacity. You shoot one bullet and it's gone.
Yeah.
You can't you get a faster reload if you have
Okay.
a certain percentage of it.
So here, are we still going?
Yep.
It's the people
Okay.
who really have fair.
So here's kind of the next big equation. And your book has it, again, your book has it like, it's the same equation, but
I
your
tried to
equation
use that.
sheet has it twice. One they write is like a matrix cross product. So it's IL times B, usually it's just written as bill sign 30, okay? That's, everybody rearranges it into bill, okay? They get technical and put, oh, ILB, it's bill. Okay? So what this gives you is the force that's gonna act on a wire that is subjected to a magnetic field, okay? Because this is what I'll show you in the demonstration in just a second. Is that, now, here's your criteria. The wire has to be in a magnetic field. If the wire is just like out in the open, there won't be any force on it. If there's no current moving, there's no force. And oddly enough, you have to have a length, okay? Because without a length of wire, oh, there's no wire. There's no force.
Where's the wire?
It's the invisible wire, okay? Now, the units get a little bit weird on this deal, they're not horrible. So, your charge is gonna be in coulombs. Your velocity is in meters per second. And, your magnetic field gets weird, because that's like Newton seconds per coulomb meter, and basically everything cancels out and you get meters. So, I'm just showing you how the units work out. So let's go to the back and I'll kind of show you how this deal works. So yeah, bring that, because this is,
Luke lady, Luke lady, there's Luke lady. Say hi, Cassie. It's Luke lady. Luke lady. Boy, oh boy.
Some like unlucky physics kid is gonna run across these in like 20 years and just
Just
hear
looking up.
your comments.
You do bust. What is this? It's gonna keep getting him subscribers. Subscriber. What is this? Oh, dude, I want to play with toys.
I would not put the camera next to this man.
Yeah, that's probably bad idea. I think that's why your cameras are breaking.
No, no, no. That's the first time I've ever put it there. Play with toys.
Okay. So what this is these wires can pivot, okay? And I've also got a little tiny compass here, right? That's oddly enough it's plain more. So when I push down on this button, what it's going to do is going to create two currents. One current on this side is going to be moving up. The current on the other side is going to be moving down, okay? So it has little flippy arrows. How cool is that? Okay. So when I do this, you'll notice that there's a couple of things. Number one, they repel each other. And then also, if you notice on this compass, when I do that, there's a deflection on that compass. So there's a couple of things that are happening. Even if I don't see anything else, I know by virtue of the fact by watching that compass and that compass needle moves, that is going to indicate that these wires are creating a current. When they create that current, I'm creating a magnetic field. So this is like a 5-step process, okay? So first thing we're going to do, we're going to start with this current over here that's going in this direction. So just act like this isn't even here, okay? It's gone. It's not even there. Do not worry about it. It's not, okay? So if I just said, here's this current, what's the direction of the magnetic field associated with this current? Current's going up, so it's going to be going into the page on that side, and it's going to be coming out over here. So we're going to call this current number 1, okay? So on this side, we're going to put X1s, okay? Then over here, I'm going to have dots, okay? I don't care about that, okay? So this current's going this way, so this is the first thing you got to be able to do. Say, okay, I got a current going this way. That's going to create a magnetic field that's going in this direction, okay? Now, we're assuming on this that it's positively charged particles that are moving, okay? So with this one, I'm going to take my thumb, which I'm assuming is a positive charge, right? And this one's going to be going down like this. So now I've got to use the second right-hand rule. So that's why I said this is like a 4-step process. So this current is coming down like this. But it's being subjected to a magnetic field that's going into the page. Okay? So now, don't worry about this wire. Okay? Wire's gone. Okay? Don't worry about it. Okay? So if I put this down like this, okay, the magnetic field is going into the page. What's going to happen?
Cancel?
It's going to feel a force going that direction. Okay? So the force on this wire created by current 1 is making it go in that direction. So here's your sequence. This current was going up. It's going to create a magnetic field going into the page here. This current, though, of positive charges is going down. It's being subjected to that magnetic field, which is going into the page, which is going to create a force going that way. Go with that. Okay? Now, let's talk about this one. Now, focus on this one. This current's coming down, right? Coming down like this. So what's going to happen to the magnetic field created by this one over here? Current's going down.
Go in.
So over here, this is going to be, okay. So this is going to be, we'll call this 2. So this is going to be X2s, right?
This is getting out of hand.
So-
Now there are two of them.
Now, these are gonna be X2s. So with this one, this current's going up, right? The magnetic field is going into the page, so the force is gonna be going this way. So this is gonna create a force going this way. So this is why when I push that button down and I create those anti-directional forces or amperes, what's happening is they're both creating forces that are pushing them apart. So this is like the opposite of everything that you've been taught so far. If you have magnets and you have a north and south pole, what do? They attract. Okay, if you have oppositely charged particles, what do? They attract. Wires are the anomaly. Okay, so if you have oppositely running currents in wires, they repel. Okay, so this is the exception to everything that you've been taught up to this point on October 11th at 2 o'clock in the afternoon. Okay, now we're gonna do a little bit of voodoo here.
It's like Mean
Or
Girls.
April. What did I say?
Wait, it's October.
Okay, we're going
I missed
back in
that.
time.
No,
I like heard
we need
that,
to move
like, it
forward.
like,
All the currents getting rid of
No, it makes sense. It makes sense.
I was thinking too hard about the other shit.
deflecting the thoughts.
That would have been
Whale hunting for your mama.
Whale?
Yeah, whaling.
Justin, what are you doing?
Burkett, we won't believe what Justin just did.
Huh? What did you do?
I didn't do anything.
Don't lie.
He's been filming that the whole time.
I currently have not been doing anything.
You have video evidence too.
No, actually, I've been keeping my hands out.
Okay,
That'd be interrupting.
now, this one, now when I do this,
Teaching myself, man.
wires are,
Attracted.
Attracted.
Interesting.
okay? So,
They must be not me and a girl.
now when you do this,
Gay wires. One species of girl that would go out with Justin.
so these are going in the same direction, right?
Yeah. I'm a cold-blooded killer. I'm going to myself.
Okay. So, current's going this way, what's gonna happen over there? X's or dots?
X's.
X. Current's going this way, so this is gonna be
Yeah. X's.
X1s.
I keep
Alright.
thinking exit wounds.
Now we're gonna do the second right-hand rule. So, current's going this way, right? Current's going this way, the magnetic field is going into the page. Current's going this way, the magnetic field is going into the page, it's gonna feel a force going towards the center. So this force,
Hang on. Why are we doing right? Oh, right hand rule. Yeah.
okay? So, this is
That's
going
not
this way. You're creating a magnetic field going into that page. Then you do the second right-hand rule. Current goes up, magnetic field goes in, force goes this way. Got that?
Yeah.
Okay. Now, this current is going this way. So what's going to happen over there? Now you're going to have dots. Because this current's going this way, so I put my hand this way, wrap my hand. So this is going to be,
I keep doing that You gotta wrap your hand around it.
So this is gonna be dot 2. Okay? So now, I take now we're gonna do the second right-hand rule. It goes up, but the magnetic field is coming
And
out of the base. I'm gonna go like this, and then I'm gonna point my fingers
and
out. So the force is gonna be going in.
this
So
is
this, oddly enough, is also creating
why is it like
an
this?
inward force. So this is why when the currents are going in the same direction, and this is what I said, this is the opposite of everything that you've learned up to this point, of April 11th, not October. So you're going like this, boom. So again, when I hit that button, you can see the compass spin. So if you have the same current, they attract. If you have opposite currents, they repel. So this is what you have to be able to think through, okay? So, got the idea. All right, back we go.
Because it just stays on one side.
Nice.
Here, instead of being a woman, you
Oh,
oh wow.
I didn't using my right hand and I wasn't going to make crap.
Sure,
Wow, Jeff.
sure. I bet you do angular velocity stuff.
I love it.
Vaughn looks like an angular velocity doer.
Huh? 100%.
Help me out here. Thank you. Your mom has just entered the building. Cassie love that joke.
Next to on even 4 weeks.
Like Tesla's oscillation machine.
They get harder and
Took your mom and mom and said, "Send me trade." Think of it. Okay, so right hand. This one. At least you were born two left hands. Though. Really good. They're both say L. I think it should just be posit instead of opposite, because we don't say opposite, we say posit.
Okay, so here's short summary. So if you have the same currents, this situation I had both going up. So here's the skill that you have to be able to do. You gotta be able to sit here and go, okay, this current going in this direction, you're gonna wrap your hand, you're gonna generate dots over here. Then, when you have dots coming over here, then because we're defining current as being a positive charge, then I point my finger up like this. It's coming out of the page. My fingers point inward. So this one over here is going to feel an inward force. Okay? So that's going to be the direction of that force. Now, the current doesn't differentiate the source of that magnetic field. So I could do a couple of things. I could either have a wire beside it that's generating that magnetic field coming out of the page, or I could just put a magnet there and have that magnet creating that magnetic field. The charge isn't going to make any difference. Okay, it's just going to go, wow, okay, hey, that's what's going to happen. where that magnetic field is coming from, okay? Whether it's created by a wire or it's created by a magnet. Now, if you reverse the process over here, you go, okay, here's this one coming up like this, current's going this way, I got X's, my current goes then in this wire, you got a magnetic field going into the page, force points this way, that's going to feel an inward force as well. So here's kind of the dichotomy, is that if the currents are going in the same direction, they create opposite directions magnetic fields, okay? Because if the currents, this one's going up, that one's coming dots. If this one's going up, that one's creating X's. So with the same direction,
You gotta flip them.
you actually create opposite directions of the magnetic field that each current is experiencing. But by creating opposite directions of the magnetic fields, that's what allows that to create an attractive force, and that's why those wires are brought together, okay? Now, the opposite happens when you have this situation. So if you have oppositely charged moving currents, this one's coming down, right? Or this one's coming up, you wrap your hand around, boom, you get X's. This one's coming down this way, over there. So if you have oppositely charged currents, or opposite direction currents, again, the dichotomy is that you create either both X's or both dots, depending upon which side, which way they're going, okay? Both X's, both dots, that doesn't make a difference, but they're both gonna be the same. But then, you do the right-hand rule here, this current's going up, magnetic field is going into the page, you point your fingers this way, it's gonna make it go out. You run your fingers this way, that current's going into the field, that one's gonna push away. So, that one's gonna push, this force is gonna push these wires in opposite directions, that's gonna force those together in the same direction. Okay? Got it?
I get it.
Good. That was really tough to show. I was able to, they actually came up with that device maybe 4 or 5 years ago. And it makes teaching this concept so much easier, because that was really tough to do when you like couldn't see like the wires like actually like moving. It's like, oh, just trust me. The kids are going,
I don't believe you.
yeah. So that was a major score. As soon as I saw that in the science catalog, I was like, Santa came early, score! Okay.
Everyone else is just like,
So-
nerd.
Yeah.
It's okay. I can respect the purchase.
Okay.
Sorry, I just had to sign on my table.
It says signing books.
I mean, yeah. The table was just off balance. What did Germany make? Was it meth? I think Germany made meth during World War I, right?
I think I know what you're talking about. No, I don't think it was some type of opioid like that. I don't know that it was
How does
meth.
this unit
It was a stimulant of some sort.
How does radius equal NV between
Germany also did.
Single what?
Maybe it was. I remember doing a speech over it in Pfeiffer's. Which is why I would remember.
Okay, what probably makes
So you
it
remember giving a speech, but you just
I
remember
had
that.
to
Exactly.
guess.
And it definitely wouldn't have been coke, because that's not fun to say. Methamphetamine is fun to say.
They also call it
Like afterwards, stuff like that.
Okay. Now, this equation is not on your equation sheet. So if you need this for the test, I will give you this equation. But basically, it's a substitution. So if you have a single current moving through a wire in a magnetic field, It's just force equals Bill, technically sine theta, but it's almost always at a 90-degree angle. So it's generally, you don't have to worry about the sine theta part. But if you look at how you can calculate that magnetic field, well, that's that equation that we came up, 2 pi d, and that's going to be the distance in between the two wires. So if you take this and you substitute that in there, u naught I over 2 pi d for that magnetic field, so this becomes u naught I, and then that first L and that L, so this is going to be that second current, and then that's just going to be 2 pi d. So all I did was take this and substitute this in here. Typically what happens is that these two currents are generally the same, okay? It's just going to be the magnitude. So, and again, if you look at this in terms of what's a factor, you have L. Obviously, if you have more wires subjected to that external magnetic field, that's going to create more force. It's inversely proportional to the distance between the wires. So if I took those wires and I moved them far enough apart, effectively, at some point, nothing's going to happen, okay? So this is why you divide by D. So, and obviously, the stronger the currents are, the more force that's going to feel, okay? Because the stronger that current is, the stronger that magnetic field is going to generate, the more intense that magnetic field is going to exist around that wire. Got the idea? Okay. So here's how this might play out. So what you can do is let's say you might have like a wire like this and a wire like this. And let's say that this has a mass of like, I don't know, 10 grams, whatever it might be. And you want to figure out, and it's separated by a distance of like 5 centimeters, okay? So you have 2 wires, separated by a distance of 5 centimeters, about like it. And this top wire has a mass of 10 grams. So you want to figure out like how much force, how much current, a whole bunch of different things you could do to make this wire hover, okay? Because clearly you've seen, wow, these forces are strong enough to make them pivot. So if I line this up just right, I can make that hover. Well, here's the deal. What would be the downward force? How could you calculate the downward force of gravity? Yeah, take 10 grams, convert that to kilograms, boom, there's your downward force, right? Okay, cool. Now, that would have to equal the force created by the magnetic fields and the currents. Well, here's the deal. If this wire is anchored, and you want this upper wire to hover, so imagine that I could take that apparatus and I could turn it sideways. And I want to make that, so I've got that bottom wire, and then I'm going to make that upper wire hover. So first off, would I want a repulsive force or an attractive force between the wires?
Repulsive.
I would want a repulsive force. So since I want a repulsive force, would I want the currents to be going in the same direction or the opposite direction?
Opposite.
Opposite, because with wires, opposites repel. So if I know one current is going in one direction, the other one would have to be going in the opposite direction. So then, depending on what you're given, oh, okay, well, if I know your gravitational force, set that equal to your force. You know how far apart they are. And in this situation, you just have to assume, if you're not told anything differently, you just have to assume the two currents are the same, okay? Now, I see this happen a lot. If you're going to do that, if you're assuming that the currents are the same, and I'm not asking this to insult anyone's intelligence, but I see it happen all the time. When I multiply I by I, what do I get?
I squared.
I squared, we don't get 2I. Okay? No, you laugh.
But
I can't
they're
tell you how many
different.
times I've seen that happen. Oh, I times I, 2I. Oh, it's not 2I, it's I squared. Oh,
What is people? Just don't know how to do
Anyway,
that.
just something to think about. Now, when you get to some of these questions on your assignment, you're gonna have to go old school circuits, okay? Currents, resistors, batteries, okay? So I'm just telling you that don't think, oh, we're done with circuits and you don't have to worry about that because you're going to. So there's gonna be two parts to your assignment. There's gonna be some questions out of the book, and then I've got a photocopied sheet as well. Let me hand out that photocopied sheet, so stop that for a second.
British people.
So let me kind of point out some things
This looks awful.
on this page. First off, notice that, like the first question, you're talking about an electron, okay? Not a proton, it's an electron, okay? So pay attention to how they're defining this system. Positive X, positive Y. Now, you have positive Z with a dot. So how are they defining positive Z?
Out.
Out of the page or into the page?
Coming out to you.
Out. So imagine this is this X and Y axis. So your X and Y, they're like in the plane of the page, and then you have a Z axis that's coming out of the page, okay? So positive X, positive Y. So when you're looking at this, realize, number one, that it's an electron. Number two, how they are defining the system. So, on question on the second question, charged particle moving through a region of space at constant speed without deflecting from this one conclude that in this region, okay? Now here's the deal. What's the two most important words on that second question? Now, there's two situations you can have an object move at constant speed. What are the two situations an object can move at constant speed?
Lack of gravity.
Either there's no forces at all, like you're in deep, deep, deep space, and I give this a push, and this thing is going to move at a constant speed because it has inertia, and there's no forces to make it stop or speed up. So situation number one, there are absolutely no forces whatsoever. Option two, I push it along at a constant speed. In that case, all of the forces add up to zero. Okay? Now, let me give you a hint.
Electrons have friction.
There's two potential ways that you can deal with charged particles. One is you can use electric fields. Okay? So if you remember the equation FEC, force, electric field times charge. Guess what? You can also create a force on a moving particle by a magnetic field. Okay? So keep that in mind. When you get to that third question, keeping in mind that that is an electron again, and it's the same X and Y, Z axis as the first one, where that Z is coming out of the page. So you got these three, there's multiple choice, no questions to answer on that one. And then your assignment out of yonder book.
Yo-yo. Yeah. Dude, I'm just gonna build different.
Infinite favor.
Do you remember the little math folder things? It was just 2 pages. Like from first grade. Like it was like a folder, but it was just 2 sheets of paper and it was math. Well, that's probably why you got Army Calc too.
I didn't go to this.
Yeah, sure. But sure. Well, yeah.
It was terrible. I was terrible at it.
Yeah, no idea.
It's alright, me neither.
So if it's moving there,
Why'd you do it?
then it must
Yeah.
be.
I thought it wouldn't be that bad.
Okay.
I got it.
When you get to question 47, this will make sense. when you get to question 47, there are 2 springs, okay? Count them, 2 springs.
2.
And remember, the force on the spring is F equals Kx. So ironically, if you teach long enough, you have things that remind you of different things. So Lucas Schauer, his dad is Coach Schauer, who coaches the wrestling team. He's in my AP physics class, and he screwed this problem up because he forgot that there were 2 springs. So I've subsequently, and his nickname was forever then 2 springs. Okay, so that was it. And it's a long story short, but because of an award that I got at KU, he's getting married because to a gal that he met at this award ceremony. They're getting married out in Colorado, so he's asked me to come out and officiate at his wedding. So it's random how things work. So yeah, so the kid I nicknamed 2 Springs, I'm going to end up officiating at his wedding in Colorado over Memorial Day weekend.
What a
So we
nerd.
got that.
Kind of a weird deal.
Uh-oh.
Yeah.
Or at least like an award show.
Marrying 2 nerds together.
Yeah. Well, I taught her as well.
Oof.
I taught Ellie Hardesty. I taught both, not in the same class, but. And the neat thing about Ellie is that I've taught for 30 some odd years. I lost one of her tests in physics. I still to this day have no idea what happened to that test. Because it was the
That's
only
bad.
time I've ever lost